Hess's law is another way to calculate enthalpy change of a reaction. Hess's law states that for a particular reaction, the change in enthalpy is the same, whether that reaction takes place in one step or in a series of steps. So the change in enthalpy is the same regardless of the pathway. We know that this is called a state function. So enthalpy is a state function. So an example of Hess's law in action here is for the reaction nitrogen plus 2 oxygen yielding 2 nitrogen dioxide, the reaction absorbs 68 kilojoules of energy. Your enthalpy change is positive 68 kilojoules. If that reaction occurred in 2 steps, where nitrogen and oxygen bonded to form 2 nitrogen monoxide, and then the nitrogen monoxide bonded with another oxygen to form nitrogen dioxide, the total enthalpy change is still the same. Reaction 1 absorbs 180 kilojoules of energy. Reaction 2 releases 112 kilojoules of energy, but overall, your net change is the same, regardless of if it took place in one step or a series of steps. When you are doing Hess's law, you might have to manipulate the equations that are the steps. And these equations, these reactions, can be manipulated in 2 ways. They can be flipped, so reversed, reactants become products, products become reactants, in which case you would change the sign of delta H, or they can be multiplied and or divided. And whatever you do to the reaction, you do to delta H. So you can do one of those 2 things, you can do both of them, you can do none of them. It's just going to depend on the reactions. So to decide how to manipulate an equation, you're going to see if it contains a species that is in the goal equation but not in any other equation. Make the species you have matched, or make the species you have chosen match the goal equation. Repeat for all equations possible, and then manipulate any remaining equations to cancel out unwanted species. Doesn't make a lot of sense until we actually do it. So what I keep referring to as the goal equation is always given, and the delta H, the enthalpy change, for that is unknown. I have equation A and equation B. And what I want to do is I want to manipulate equation A and B so that when I add them, A plus B, I get the goal equation. And so to do that, I need to focus on just one species in each equation. So in equation A, I have sulfur, oxygen, sulfur dioxide. I need to choose which one to focus on. Just focus on one instead of the whole equation. It makes it a lot easier. I don't want to pick the sulfur dioxide because the sulfur dioxide is also in equation B. And so what I would have to do is figure out what to do to A and B to end up with no sulfur dioxide in my goal equation. Don't want to pick oxygen because that's down there as well. I'd have to figure out what to do to A and B to get 3 oxygens. So that's pretty hard. Sulfur, solid sulfur, is not in equation B anywhere and is in the goal equation. And so I'm going to pick that one to focus on. And I'm going to make the sulfur in equation A exactly match the sulfur in the goal equation. When I say exactly match, it has to match the same side of the reaction, and it has to have the same coefficient. Okay, so in reaction A, the sulfur is a reactant. In the goal equation, it's a reactant. So that's good. I don't have to worry about that. In the goal equation, however, there is a coefficient of 2 in front of the sulfur. And so what I'm going to do is I'm going to multiply the whole reaction A by 2. And I'm going to rewrite that 2 sulfurs plus 2 oxygens yielding 2 sulfur dioxides. Whatever you do to the reaction, you do to the delta H. So multiply the delta H by 2, you get negative 1188 kilojoules. In reaction B, I kind of already went through why you don't want to pick the sulfur dioxide or the oxygen to focus on. I'm going to focus on the sulfur trioxide. And I'm going to make that match the sulfur trioxide in my goal equation. Again, has to be the same side, has to have the same coefficient. They do have the same coefficient, but in the goal equation, sulfur trioxide is a product. In equation B, it's a reactant. And so when it's on the wrong side, this is the instance where you would flip or reverse that reaction. So I'm going to rewrite equation B reversed, where the sulfur dioxide and the oxygen are reactants, and the sulfur trioxide is a product. I need to put my states in. Because I reversed the reaction, the sign of delta H flips as well. It was positive 198, now it's negative 198. Once you have done this, you want to make sure that when you add A plus B, you do end up with your goal equation. To do that, you first will cancel out anything that you can. If things are on two opposite sides of the equation, so if it's a reactant in one equation, a product in the other, it will cancel as long as they have the same coefficient and are in the same state. So I have two gaseous sulfur dioxides as a product in equation A and two gaseous sulfur dioxides as a reactant in equation B. Those will cancel. If things are on the same side, like the oxygens, they don't cancel. They just add. So I can't cancel anything else. I'm going to rewrite what's left. So I have two solid sulfurs plus three oxygens yielding two sulfur trioxides, which, hey, is my goal equation, which means you did this correctly. So you can go ahead and add your delta H's. And really that delta H is the answer. Negative 1386 kilojoules. It's not a question mark anymore. Now it's negative 1386 kilojoules. I solved for that. But you do want to add the reactions as well, just to make sure that things cancel and they add together to give you the goal equation. So let's look at another one. So here's my goal equation. Here's my delta H. When I'm trying to decide what to choose, I don't want to pick O3 because there's O3 here. There's no O3 up here. I don't want to pick O2 because there's O2 here and no O2 up there. So that would be very, very challenging. So we're going to just ignore equation A for a minute. Let's look at B. Don't want to pick O2 because it's in A and C. That makes it hard. But this 2O, monatomic oxygen, is only in equation B. It's not in A, it's not in C. It's only in equation B, and it's in the goal equation. That's what you're looking for when you're trying to decide what species to focus on. So this 2O, I'm going to make match that O. Same side, same coefficient. So the first thing I notice, it's on the wrong side. In the goal equation, it's a reactant. In equation B, it's a product. So I am going to flip this reaction to get it onto the reactant side. The other thing you notice is that there is one O in the goal equation. There is two O's in equation B. So we're going to multiply it by half. So I'm going to leave a space for A. I'm going to rewrite B, flipped n times half. So O gas produces 1/2 O2 gas. I reversed the reaction, so that changes the sign of delta H. I multiply the reaction by 1/2, so I do the same to delta H and get 247.5 kilojoules. Equation C, I can actually pick the NO or the NO2. It does not matter at all. I will pick the NO. I will make it match that NO. But if you pick the NO2, it's this, you're going to get the same thing. They are on the same side. They do have the same coefficient. So I'm actually not going to do anything to C. I'm just going to rewrite it exactly as it was up above. Oops, NO2 gas plus O2. I didn't do anything to the equation. Don't do anything to the delta H. All right, that brings us back to A. So I don't have O2 or O3 in my goal equation. And so the steps that I had done before here, the last step said manipulate remaining equations to cancel out unwanted species. So that's what I have to do now. I have to manipulate A to cancel out the O2 and the O3. And again, what you pick here is going to determine how easy this is. If I pick O2, I got O2 here and here. And so I'd have to figure out what to do to equation A to cancel both of those O2s. If I pick O3, however, I only have O3 right there. And so that's a little bit easier. Now to cancel, they have to have the same coefficient. So I'm going to multiply this by 1/2 so they get the same coefficient. But they have to be on opposite sides. When they're on the same side, they add. When they're on opposite sides, they basically subtract. Right? So if I have 103 minus 103, I have 0 O3s. It cancels. So to get that O3 onto the product side, I need to also flip equation A. So I'll rewrite this flipped n times 1/2. Do the same thing to my delta H. So flipped becomes positive times 1/2, 213.5. All right, now I have to cancel. My O3s cancel. That's the whole thing that I just did. I have 3/2 O2. And then in equation B, I have 1/2 O2. So that 1/2 will cancel. 3/2 minus 1/2 is 1. So I have 1 O2 left. That O2 will cancel. Nothing else cancels. Let's see what's left. I have gaseous O plus NO yielding NO2, which is my goal equation. Hooray. So then I just add my delta H's to get my final answer, negative 233 kilojoules.